Hi once again, senior high students. It's me, Miss Leia, and for today's video, we're going to talk about uniformly accelerated motion. Now, for the Lasallian guiding principle, I'd like you to be able to participate responsibly in the world of work, family, community, nation, and church. For you to, maybe you can be instrumental in preventing something like this from happening. It's the Montparnasse train derailment in Paris, France, and we'll talk more about that in our synchronous discussion about UAM. For the learning targets, we have a total of 5 for this particular lesson, but in this video, our focus will be on the first one. I want you to be able to describe a body that undergoes uniformly accelerated motion, briefly known as UAM. Now, first, I want you to recall that acceleration is a vector quantity which simply refers to the rate at which an object changes its velocity. In mathematical form, it's delta v divided by time, or change in velocity per unit time. Now, we have this specific case of acceleration, and we call it uniformly accelerated motion, which is the focus of our discussion for today. It is the state of motion wherein an object changes the magnitude of its velocity at a constant rate. So how does that look like in a more concrete way? I'd like you to consider this car as an example. And I want you to notice the change in the velocity of the car, as shown. Let's say, for example, in the first interval, 0 second to 1 second, it was initially at rest, so it starts with 0 meters per second, and after 1 second, that velocity became 5 meters per second. So what do you notice? In 1 second, the velocity increased by 5 meters per second. Did the same change happen in the next intervals? We'll see. So let's look at the next interval. That's another 1 second interval, just like what we observed earlier. And we can also see that the velocity of the car changed from 5 meters per second to 10 meters per second from point A to point B, which means that the same change happened. The magnitude of the car's velocity increased by 5 meters per second because 10 minus 5 is 5 meters per second. Going forward, from 2 to 3 seconds, the same change happened, right? That's another 1 second interval, and the change in velocity is still 5 meters per second because 15 minus 10 is 5 meters per second. So the velocity is still changed at this point by 5 meters per second per 1 second interval. Going forward, you can also see that this is another 5 meters per second increase in the velocity within another 1 second interval from 3 to 4 seconds. And lastly, it's the same thing. The velocity changed from 20 meters per second to 25 meters per second within another 1 second interval. So you can see that the magnitude of velocity increases by 5 meters per second every second. It's the same increase throughout the entire trip. And in other terms, we can also say that the acceleration is constant at 5 meters per second or 5 meters per second squared. Because if you can still remember, acceleration is the rate of change in velocity per unit time. Therefore, if the velocity increases by 5 meters per second every second, the acceleration is 5 meters per second or 5 meters per second squared. And that's what UAM means. When we say uniformly accelerated motion, the object changes the magnitude of its velocity at a constant rate, just like this one. Every 1 second time interval, the change in velocity is always 5 meters per second. It always gains a speed of 5 meters per second every 1 second interval. Going forward, I'd like to debunk a few misconceptions about this topic. First one, some students would say a body in UAM has constant velocity, which is wrong because the velocity is not constant if an object is in UAM. That's why it says accelerated motion. So it's accelerating. A body in UAM is accelerating, but the change in the velocity it experiences is constant. Like this one, the change in velocity is always 5 meters per second. Okay, so that's wrong. Another misconception, a body in UAM has changing acceleration. It's also wrong because if an object is in UAM, the acceleration is constant. Like in the case earlier, the acceleration was always 5 meters per second every second. Okay, now Is it convenient to study about UAM when the discussion is about accelerating bodies? The answer is yes, because bodies normally accelerate uniformly. Example, car engines are designed such that the car has a definite power rating measured in horsepower, right? Okay, so most bodies accelerate at a constant rate because they're limited by what their engine is, okay, in the case of cars. So given their certain power rating, they can only accelerate at a certain rate, okay? It may not necessarily be exact, let's say exactly 5 meters per second squared, but something close to that value every time it accelerates, okay? So it's because of their engine design. And for humans, it's also the same case. Let's say, for example, humans have unique physique, they have unique trainings. An athlete, for example, after years of training and muscle building, he or she would have a definite acceleration rate, okay? And another person who has, let's say, less training, who has a different physique, would also have a certain value of acceleration that he is capable of maintaining. Going forward, how about bodies that don't accelerate uniformly? We're not going to study about them because they require more complicated math. Let's say, for example, the turbulence being experienced in aircrafts. That's an example of non-uniform acceleration, and the math behind that is complicated. So for simplicity purposes, in high school, we just teach uniform acceleration, okay? Just like the example I showed you earlier with the car.